Hello everyone. So this is the first lecture in the series of tensors, and my goal here is to introduce tensors in a way which is useful for those who wish to learn general theory of relativity. General theory of relativity requires the knowledge of tensor. So what I will be doing is start with the abstract definition of tensor, and then slowly in the future videos I will be developing all the transformation laws that are useful to do all sorts of calculation in the context of general theory of relativity. So before I start in this lecture, I'm only going to introduce the definition of tensor. Now there is some prerequisite for it that you must know what is a vector space, how do you define the vector space, the concept of linear independence, and the basis of the vector space. You can look up any standard textbook of linear algebra for this. It's not that difficult to understand. So make sure you know the definition of vector space, linear dependence, independence, and the basis of the vector space. From there, I will start. So today, I am only going to introduce the definition of tensor, and tensor comes in all sorts of different forms. They can be defined in several different manners. But keeping in mind what is my goal, I will give the definition which is most useful in the context of studying general theory of relativity. Okay, so let's start. So let's say that you have your vector space, you have your vector space V. So V is your vector space, and this is a finite dimensional vector space. So let's say dimension of V is n. And one more thing, this is a vector space over R. So this is your real vector space. Okay, that's what I am taking. Then consider the following set. What is the set? The set of all the functions f defined over the vector space V and going to the set of real number R, such that what is the property of these functions? Such that this function f is linear. Okay, now this set is denoted by V star. Okay, and it turns out that if you define, right now this is just a set. If you define two operations here, two operations, first one is the pointwise addition. Pointwise addition of functions, and the second is the scalar multiplication. Then with these two operations, this set V star forms a vector space. Now, showing that this set that we just defined V star with these two operations forms a vector space is a very easy exercise of linear algebra. So please do it. This is an easy exercise, and if you have not done the vector space before, so when you are doing the vector space, do this exercise. It will help you to understand the definition of the vector space. So this V star that we just constructed by making the functions over the vector space V, this is called dual space. So V star is called dual vector space. And the elements of V star are called dual vectors. Dual vectors. They are also called or covectors or functionals. So if someone is coming from the pure mathematics background, then in their linear algebra course, they have studied the functionals. That's what they use. In general relativity, you usually say covectors. Okay, so that's the thing. Now, for every vector space, for every finite dimensional vector space, we can construct this V star, this another vector space which is known as dual space. We can do that. I hope you understood everything up to here. Okay. So now, since V is your vector space and it's a finite dimensional vector space, so it must have a basis. So now let's say, let V1 up to and so on Vn, this is the basis for the vector space V. Be the basis of V. Okay, V is a finite dimensional vector space, so this is the basis. And let's say you have these elements from the V star, V1 star up to and so on Vn star. These are the elements coming from the corresponding dual space. And these are not just any element. These are the elements with some property. What is the property? The property is that if you take any element of these, that means if you take any V mu star and you operate it on some basis vector V nu, okay, on some basis vector of the vector space V. So this V nu is coming from this set, this basis of the vector space V, and V mu star is coming from these elements of the V star. Then this thing is equals to the so-called chronicle delta, delta mu nu. What is the chronicle delta? Delta mu nu is 1 if mu is equals to nu and 0 otherwise. Okay. So what I have done till now, I know that the vector space V is a finite dimensional vector space, so it has a basis. So I have taken a basis from V1 to Vn. This n vector forms a basis for V, and I have picked up n elements from the corresponding dual space V star. And those are not just any n elements, those are the n elements which satisfy a certain property. What is that property? That if any of that elements V mu star operate on the basis vector V nu, then it gives you delta mu nu, which is the chronicle delta. Now, there is something interesting about it, and you might guess what's gonna happen, what I am doing. There is a reason why I have taken only n elements from the V star. So let's do certain things. So I am going to make first claim here. What is the first claim? First claim is that this set of elements that I have taken, V1 star up to and so on Vn star, this set is linearly independent. So this is the first claim. Let's prove it. It's a very simple proof. So let's do that. What do I need to show? I need to show these vectors in this set are linearly independent. How do I show the linear independence? Well, for that, let summation alpha mu v mu star is equals to 0 and mu runs from 1 to n, and where these alpha mu are scalars coming from set of real number, because I have taken the vector space over real number. So what I have considered here is the linear combination of all these elements of the dual space, and I have put that equal to 0. Now what I need to show for the linear independence, that all these scalar alpha mu are 0. If all these scalars alpha mu are 0, then I can say that all the elements in the set, these v1 star to vn star, are linearly independent. That is the basic definition of the linear independence. Now one thing, on the left hand side here, I am taking the linear combination of these functionals of covectors or dual vectors. So on the right hand side, this 0 is not just a number, it's a 0 functional, like a 0 map or 0 operator. So like that, this is a 0 functional. So here, this thing, it is a 0 functional. Please don't get confused with the wordings. Okay, functional, covector, dual vector, one and the same thing. So this is a 0 functional. Now, you already know the properties of these elements. What is that property? We will use that property. That property is, when it's operate on some basis vector, it gives you delta mu nu. So since on the both sides you have your functional, on both sides you have the functional, so why not operate by some basis vector on both sides? What that will give us? That will give us summation mu equals to 1 to n alpha mu v mu star v new is equals to 0, because when 0 operator will operate on something, it will give you 0. Okay, so this will give us summation mu equals to 1 to n alpha mu, and this will be by definition your delta mu nu equals to 0. Now here sum runs over mu equals to 1 to n, and we know that Kronecker delta is 0 for mu not equals to nu. So for mu not equals to nu, all the terms will be 0. The only term that will be non-zero is when mu is equals to nu. So this implies that alpha nu is equals to 0, and nu is just any index. It is taking value. Nu is any index, it's just the index. So this is true for any nu. So all the scalars are 0. And if all the scalars are 0, then that means thus this set of v mu star, where mu runs from 1 to n, is linearly independent. Okay, so my first claim is proved. Now I'll make second claim. What's the second claim? The second claim is that this set v1 star to vn star actually spans v star. What does that mean? When do I say that some set spans an entire space? When, if I take any element of this V star, then I should be able to write that element as a linear combination of the elements of this given set. What I am saying? What I am saying, so I will prove this also. What I am saying that if I have some element, let's say V star belongs to V star, and if it is indeed true that this set from V1 star to Vn star spans V star, then then I should be able to write V star as a linear combination of these elements V mu star, right? But note that I will be able to do this only when I can find such scalars, alpha mu. So this is the question. Does there exist? So this is a question mark. Does there exist such alpha mu's? This is what we need to show. To show that this set actually spans V star, the dual space, the only thing I need to show the existence of a scalar for which any element of the V star can be written as the linear combination of the elements V1 star to Vn star. Okay, so let's say, suppose it is possible. Suppose it is possible, and let's find those scalars. So if it is indeed possible, then I will be able to write it like this. And again, this is a functional. Here, this is an entire linear combination. We can operate it on the basis vector. So let's do that. So V star operates on some basis vector V nu. So this will be summation mu equals to 1 to n alpha mu V mu star V nu. And just like we did above, this thing V mu star operating on V nu will give you delta mu nu. And for all mu not equals to nu, this will be 0. The only value that matters is mu equals to nu. So this will be equals to what? This will be equals to alpha nu. And mu is just index. So you see what we got? The scalars for which this thing is true. Those scalars are nothing but the value you get when you operate your functional on V nu. Okay, so if we take alpha mu equals to simply f of V mu. Please don't be confused by the notation. Just to write it simply, you don't get confused. I have used f for the elements of V star. Okay, just so that you don't get confused. You can also write or you can simply write V star V nu. You can write this also. Okay, there is no problem. So if you take these scalars, then any element V star of the dual space can be written as a linear combination of these V mu star, where mu runs from 1 to n. This will be true for all, V star belongs to V star. And if it is true for all, V star belongs to the dual space, then this means this set V mu star actually spans our dual space. Okay? And if you know, so we have shown two things. What is the first thing was that this set of elements is actually linearly independent, and this set of elements spans V star. Well, what does this give you? This gives you the final result that this V1 star up to and so on Vn star such that V mu star V nu equals to delta mu nu forms a basis for the dual space V star. That's what it means. Because what is the basis? Basis is a set of linearly independent vector which spans the entire space, and that's what I have shown. And the cardinality of the basis is nothing but the dimension. Here cardinality is n, so the dimension of V star is n, which actually is also the dimension of the V, the vector space, corresponding to which this is the dual space. So these dimensions are same. So I hope you understood all of this up to here. All this construction of the V star, I hope you have understood. But you see, one more thing, what I did here, I took the vector space V and using that I constructed this another space which is V star. But V star is also a vector space. So you see, what I can do is that I start with V star. Earlier I started with the vector space V, but now since V star is also a vector space, what I am doing is I am going to start with V star itself. Because V star is also a vector space, so I can make the dual space of this V star. Okay, let me write down what I am saying. I can do the similar construction can be done by starting with V star, as V star is also a vector space. So earlier we started with the vector space V and formed V star. Now we are starting with V star. So now what will be our set? This will be V star star. There earlier we had the function f going from V to star because we started with the vector space V. But now we are starting with the vector space V star, so this will contain the function from where to where? From V star to R, such that f is linear. Okay, this is known as the double dual. This is called double dual, dual of the dual space. Now there is a theorem, very important theorem. I will not prove it here, but the proof of this theorem is very simple. and you can look it up in any standard textbook of linear algebra. So what is this theorem? The theorem is that for a finite dimensional vector space, for a finite dimensional vector space, V, the double dual that is V double star is isomorphic to V. Okay, proof is quite simple, so have a look at it. See, doing the proof of these things, these simple little proofs, are really a good intellectual exercise. It might seem too abstract and everything, but understanding something deeply is a great intellectual exercise. So we must do that. So now we have all the tools which are required to define a tensor. So now we are going to finally define what this lecture is about, and that is our tensor. So let's define that. Definition. So a tensor T of type K, L over the vector space V. So this is your vector space and this is a real vector space. So I'm going to write it like this. This is a vector space over R, real vector space. So a tensor T of type K, L over the vector space V is a multilinear map So what is this map? This map is T V star cross V star cross V up to and so on cross V, and this goes to R. So here I have K copies of V star and L copies of V. Now you might say, can we take the product of the vector space V first and later the product of V star? Of course you can. And this is a convention. So before you read the tensor from any other book or any book, make sure if you are reading general relativity from some book, let's say, then make sure what convention they are using. Because if you take the product of V first and then V star, then certain things will change. Certain notation might change or certain things will definitely change because everything is defined according to the main definition. Everything is done according to the main definition. So in main definition, in which order they are taking the product, it is necessary to know that. If they are taking the K copies of V star and L copies of V, or K copies of V and L copies of V star, you need to make sure before doing anything else from the book which is based on tensors. If you pick any book to read a concept which is based on tensor, go into the chapter on tensors and make sure you know the convention. that what convention they are using. So that's it. That's what tensor is. A tensor is a multilinear map which is defined over the product of the vector space and the dual vector space going to the R. In general, on the codomain, any field can be taken. But in the context of general relativity, the field that we take is the field of real numbers. That's what I'm doing here. Okay, and I hope you understand the meaning of linearity. I don't need to do that. Just like in case of linear transformation, if you have a linear transformation, what linearity meant? The linearity meant something like alpha v plus beta w. This is equals to alpha t of v plus beta t of w. So just like this is the meaning of linearity in case of single variable. Here you have more than one. So in each variable, this is linear. Take the element of v star, then second v star, then the third v star, some element of v, next element of v. So in each entry, it is linear. That's what it means. So now, according to this, let's see what is a 0-1 tensor. What is a 0-1 tensor? What is it? So a 0-1 tensor, what will be that? A 0-1 tensor will have 0 copies of v star and just 1 copy of the vector space v. So this will be a map going from v to r. You remember it? What is this? This is the element of the dual space going from vector space to r. So this is nothing but is a dual vector. Dual vector or co-vector or functional. So dual vector or co-vector or functional is nothing but a 0-1 tensor. Okay. So now let's have a look at 1-0 tensor. What is a 1-0 tensor? Now 1-0 tensor will have 1 copy of v star and 0 copy of v. So what is this? This is an element of what? Double dual. That is v star star. Now note that I just told you the statement of a theorem. What was that? The theorem was that this double dual v star star is isomorphic to v. If these two are isomorphic, then what that means is just a vector. Elements of v are called vectors. So if it is isomorphic to this is nothing but a vector. So this thing tells you that this t going from v star to r is a vector. So what you have here is another way of looking at a vector. Vector is nothing but an element of double dual or a map from a dual space to real. That's what a vector is. Okay. So now let's have a look at 1-1 tensor. What's a 1-1 tensor? So 1-1 tensor will have 1 copy of v star and 1 copy of v going to r. That's what the 1-1 tensor is. Okay. Now let's do something. What I do is I fix an element of the vector space v and I define another map. What is this? This, using this map T, I am constructing another map. What I am doing, this T has two slots, one for V star and one for the V. So I leave the slot for V star open and I put this V here, this fixed V here. I have taken a fixed element of the vector space V that is here, but I have left the slot for V star open. So now from this T, which had two slots, two variables, I have constructed another map which has only one variable. So this is a map going from V star to R because the slot for the vector space V is fixed. It's not changing. The only slot which has different values is the slot for the V star. So this is going from V star to R. And then you clearly know this is the element of double dual. And how it is identified? With this element of the vector space V. And it is identified with with an element of the vector space V. That's what I have done. Using the map, using this map T, which is a 1-1 tensor, I have constructed another vector. Using the 1-1 tensor, what I have constructed a vector. I just told you in case of 1-0 tensor, 1-0 tensors, these are the map from V star to R. These are nothing but vector. So, so, so what I have done here is if you are given an element from the vector space V and your 1-1 tensor T, then that 1-1 tensor T produces another vector in V in a linear fashion because it is still linear. This element of V double star that I created using the 1-1 tensor is still linear because it was already linear in both the slots. I have just fixed only one slot. In other slots, it is linear already by the definition, by the way it is constructed. So what you are having that for a given element and given 1-1 tensor, it can produce another vector in the vector space V. That's what's happening. So similarly, one more thing. I will discuss it in length in later videos, but right now I'm just giving you the definition. 0-2 tensor. What will be the 0-2 tensor? And I will denote it with a different. Okay, let's first do with T. So 0-2 tensor will have 0 copies of V star and 2 copies of V. Right? Now, V is a vector space. Take your vector space to be the TPM, the tangent space at the point P of the manifold. Then your 0-2 tensor will be this, right? And this 0-2 tensor is nothing but your so-called metric tensor. A metric tensor is a 0-2 So